Makai just asked what our additional break day assignment is going to be, and I said I hadn't decided yet, but I will definitely let you know before the weekend. And it will be something to do with this class. Perhaps. Well, it might have something to do with optional test preparation that you might have chosen to do anyways, but certainly isn't required. I encourage it though. Riley also reminded me that I've had a busy week, which continues, and I haven't updated the website. And I had that multi-page sort of angular momentum and hydrogen worksheet that we've been going through assigned as due tomorrow, but we're actually going to talk about the last section, I think, today and do it together. And if you want to think about it anymore, I changed the due date to Monday. So just finish it to your satisfaction, but really we're going through it kind of one section at a time. So if you have any questions on that, ask about it today. We'll look at those last pages, I'm assuming. We'll see. So we were talking about spin. This seems like a never-ending chapter. It's a long time ago we were talking about spherical harmonics and that kind of stuff, but the spin section, I mean, we still got a substantial amount of stuff to talk about just in section 4.4. But we said we found out that these two operators, just like in the orbital angular momentum case, L squared and LZ commute, so S squared and SZ commute. And therefore, we can find a set of simultaneous eigenvalues of these. They're both, eigenvectors of these with different eigenvalues for SZ. Of course, they're going to have the same eigenvalues for S squared. And since we're treating a spin 1/2 case, there are only two different values of SZ, and that means there are two basis vectors. And so we ought to be able to write just the spin state, ignoring all the spatial wave function stuff that we've been concentrating on for the rest of the course. We don't really care what the electron's doing in space or whatever this spin 1/2 particle is. We're only focusing on its spin state, and there ought to be two basis elements. We ought to be able to find a set of eigenvectors, simultaneous eigenvectors for both these operators, and there are two basis elements, so why not write them as a column vector with two elements in it? And each one of those is going to be a state of definite S squared and definite SZ. So if we have the most general linear combination of those, right? If I write the column vector with an A and a B in it, that means A times the spin up along the Z direction state plus B times the spin down along the Z direction state for the spin 1/2 particle. And so we have two different measurement outcomes for SZ. They're plus or minus h bar over 2. And the probabilities are simply, so I'm going back to our old thing that we've been talking about for a long time in this course. It's easy to lose track of it when we're talking about these abstract, just two element vector spaces. But if you want to know the probability associated with a certain observable, expand the state as a linear combination of those observables, and the probabilities associated with those different measurement eigenvalues are the expansion coefficients magnitude squared. So here I said if I'm in a certain state, spin state at a certain time, and I write it as a linear combination of two definite SZ states, then the expansion coefficients magnitude squareds are the probabilities. So that is to say, I can immediately see if I'm in this state and somebody says, what's the probability of measuring SZ equals plus h bar over 2? Oh, it's the magnitude of A squared. And similarly for minus h bar over 2 being the magnitude of b squared. And there's only one spin value for this because it's an immutable spin particle, spin 1/2, and therefore s squared has only one value, possible 3/4 h bar squared. Okay, so that's all easy to see. The intuition may be hard to, maybe easy for your intuition to fail when you're thinking about this, but the answers are easy to read off of that once you know what to do. Here's a substantial problem that we ended with at the end of last time. We didn't get started on it. Suppose again that we're in some state, we're biased towards the z direction for whatever reason. We've picked a direction in space and we'll call that the z direction. And this is, the sort of upstairs is associated with spin up along the z direction, and downstairs associated with spin down along the z direction. And now we decide not to measure the z component of spin, but rather the x component of spin. We measure the spin component, spin angular momentum component along some perpendicular direction, which we call x. What are the possible outcomes and what are the associated probabilities? And we've got to hang on to this thing in the box there. What I need to do is, if I want to find the probabilities, so here my observable is Sx. I want to find the various possibilities for measurement outcomes of Sx and the associated probabilities. What I have to do is write this state as a linear combination of states of definite Sx, which is to say I need to find the eigenvectors of the operator Sx. And we worked hard last time to find the matrix elements for Sx. So we've got to expand in terms of the eigenvectors of Sx, and then we can find the probabilities associated with each eigenvalue. So here's how we're going to start off, and I'm going to have you finish up this problem on the worksheet. I'm saying that my first job is to find the states. I'm just going to call them alpha, beta. Again, this is in the SZ. We're biased towards SZ when we're writing it this way. The upstairs is associated with SZ equals spin up, and downstairs spin down. We apply the matrix associated with Sx that we found to alpha beta, and we're going to demand that we get something proportional to alpha beta back again. That means alpha beta is an eigenvector and lambda is the associated eigenvalue of the Sx operator. You may not remember, but here are the matrix elements that you did on the worksheet last time to find the matrix elements associated with Sx, again, in this Sz spinor basis. So doing the usual thing where I multiply this out, or rather, I could think of this, lambda times the identity times alpha beta. So this is the same as putting lambdas along the diagonal, and then I could subtract everything off onto the left-hand side. This is an equivalent equation. And maybe you just remember the upshot of this, but when this is true, one of two things has to be true. Either alpha beta is the zero vector, and we're not interested in that case because that would mean it's not an eigenvector, right? Or the determinant of that transformation matrix that's sending it to the zero vector there has to be 0. And most people just kind of memorize that. What do you do to find the eigenvalues? You subtract off lambda along the diagonals and take the determinant and set it equal to 0. Right? That's something hopefully you've seen before, if nowhere else in differential equations, I think, where you talk about eigenvectors and eigenvalues in there. Okay, so let's take the determinant of this. When I do this one times this one, I get lambda squared minus this one times this one minus h bar over 2 quantity squared equals 0. And so that's easy to solve. I don't have to do any quadratic formula or anything. Lambda is plus or minus h bar over 2, which shouldn't surprise you because our z direction was kind of made up to begin with, right? We just arbitrarily picked a direction in space. We said we're going to call that the z direction. And we knew that the possible values of spin angular momentum were plus or minus h bar over 2. Now I'm labeling some perpendicular direction x I've chosen. And what are the possible values of x spin angular momentum? Of course, plus or minus h bar over 2. The same thing is going to be true for y, but we're going through the mechanics of it. So we've done half of the problem we set out to do. We found out what the eigenvalues are of the SX operator. Now we want to find out what the eigenvectors are as 2-element column vectors. So we can expand our initial state as a linear combination of those states and find the associated probabilities. So let's look at the worksheet. It has spinners at the top of it. We've done the front page, but we're now on the back page, problem 3. Find the eigenvectors of SX operator corresponding to the 2 eigenvalues plus h bar over 2 and minus h bar over 2. Are my eyes deceiving me that is, well, okay, I just couldn't see the bar on there. I thought it said h over 2, but it's definitely h bar over 2. Anybody missing this worksheet? I've got one extra copy sitting around. We're looking at problem 3, finding the eigenvectors associated with the 2 eigenvalues I just showed you there. So if you're having trouble getting started, remember, once we know our 2 possible eigenvalues, we take them one at a time and we write down Sx, we write down the eigenvalue equation. Sx, which is h bar over 2 times 0, 1, 1, 0, operating on the unknown vector alpha beta, which we want to solve for what alpha and beta are. Sx operating on that vector is equal to lambda, and we're taking the case plus h bar over 2 times that same vector back again. And we find out that tells us something about a relationship between alpha and beta. So see what that relationship is, and then normalize the eigenvector as usual. And we do the same thing for the other eigenvalue. Okay, the 2 cases aren't too different. Let's go to the board now. So here's my operator Sx, just that we have from the front of the worksheet. And we're writing down the eigenvalue equation, which is Sx operating on this unknown vector that we want to find out is lambda times that. And we're choosing the case lambda equals h bar over 2 first. And well, in this case, on both sides, I have a common factor of h bar over 2, so I can just sort of cancel that out. And this is really two equations, right? I have an upper element and a lower element. The upper element would be 0 alpha plus 1 beta. So beta equals alpha. And if you know something about eigenvectors and eigenvalue equations, you'll know that the last one is always not linearly independent of it. If I do the second one, I get 1 alpha plus 0 beta, or alpha equals beta. I get the same exact equation back again. So no new information from the last equation. So what we found out is that beta equals alpha. Certainly one case that works out is 1, 1. That's just not normalized, right? This is a case where beta equals alpha, but it's not normalized. So how would I normalize it? What factor do I need out in front or in either one of these positions? 1 over root 2, right? If I want to normalize it, so if I said, here's a case that works, but it's not normalized. What I would do is say, when I take the inner product of this vector with itself, remember, when we take the inner product of a finite dimensional vector space, we do the row vector with everything starred, but it's all real, so we don't have to star anything, times the column vector like that. That's going to be 1 times 1 plus 1 times 1, which is 2. And that's going to be, so the length of this vector squared, this is going to be the magnitude squared of the length is 2. And that means we need a 1 over root 2 in front. Or another way to do it is to say, let's put an a out in front. If I put an a out in front of this and an a out in front of that, then I would get a squared times 1 times 1 plus 1 times 1 times 2. And I want that to be equal to 1. I'm going to demand this. That's my notation. I'm going to demand that that's equal to 1, and that means a equals 1 over root 2. So it looks like our eigenvector corresponding to plus h bar over 2 is 1 over root 2 times 1, 1. Or I could just say 1 over root 2, 1 over root 2, doesn't matter. And Griffiths denotes this by some special notation. It's not a z spin angular momentum eigenvector, it's an x angular momentum eigenvector, but still in the z kind of basis, right? We're sort of biased towards the z direction when we write it in this 2-element way. So he denotes this by, since we have two possibilities, one of them's plus and one of them's minus, we put chi with a plus, but to remind us that it's associated with an x measurement, he puts x in parentheses up there. Okay, it's a perfectly reasonable way to denote it. So that is the eigenvector that's associated with the eigenvalue, where Sx is equal to plus h bar over 2. Maybe I'll put a box around that. That's what we found out from the first equation. Second equation is not too much different. Again, the h bar over 2's cancel, but we have that extra minus sign out there. So the upper position equation says that beta equals minus alpha. And the second equation says the same thing. Beta equals minus alpha. So that means either 1 minus 1 or minus 1, 1, doesn't matter which one we say. And then to normalize it, we need a factor of 1 over root 2 again. So in this case, we found what Griffiths would denote as chi minus associated with the x direction. I should have put an equal sign there. I'm not sure why I didn't do that. Is 1 over root 2. One possibility that works is 1 minus 1. That's a beta that's the negative of alpha, and I've normalized it. And that's associated with a definite value of Sx of minus h bar over 2. Okay, so those are our two eigenvectors and eigenvalues. Any questions on that work? That's the kind of stuff you should be able to do. I can't remember, but hopefully on the third homework, there's something like this. I can't remember if the third chapter 4 homework, which I have yet to post, but I will post soon. I think there's some things we haven't talked about on it yet. Okay. So, all right. So that was just a step along the way towards the answer to a question. Suppose at time t equals 0, say, we're in some arbitrary state, A, B. Maybe I give you the numbers A and B, and you'll find on the worksheet problem that I give you a definite state. And we want to expand, and we say, if we're in this definite state, what are the probabilities if I measure Sx that I get plus h bar over 2 or minus h bar over 2? I found the possibilities, now I want to find the corresponding probabilities. And the answer is, I have to write this AB as a linear combination of these two normalized states, right? As a C1 times this plus a C2 times this, and find what the C1 and the C2 are. Let's write that down. And then the probabilities that I'm looking for, so let me erase this stuff. I'll unshare the screen. If I have some arbitrary spinor state chi at time t equals 0, we'll write it in 2-element notation later. And I want to find the probabilities associated with a measurement of Sx. I have to write it as a linear combination, say, I don't know what to call this, C1 times the state of definite Sx associated with eigenvalue plus h bar over 2, plus C2 times chi minus x, which is to say, if somebody gives you these numbers, you have to write that as C1 times what we just found out is 1 over root 2, 1 over root 2, or I could put the 1 over root 2 out in front, plus C2, 1 over root 2 minus 1 over root 2. And then if I can find those, that's a matter of solving this system of equations, then the magnitude of C1 squared is the probability associated with finding Sx equals plus h bar over 2. And similarly for the magnitude of C2 squared. So that's what the last problem on the worksheet is. Find the probabilities associated with the two Sx values. And here I've given you a very particular initial state. So I've told you these values A and B here, and they are 1 over root 5 and 2 over root 5 upstairs and downstairs. And you can check that that's normalized in your head. And so let's figure out what those expansion coefficients have to be, and then figure out what the probabilities are. Okay, let's do the solving together. Again, this is just one way to write a system of two equations. We have an upstairs equation and a downstairs equation, because when vectors are equal, that means each component has to be equal on both sides. So this, the first equation, or the upstairs equation, says 1 over root 5 has to be equal to C1 over root 2 plus C2 over root 2. And since I really don't like the root 2's on this side, I'm just going to multiply both sides by root 2. And that tells me that C1 plus C2 has to be root 2 over root 5, which is root 2/5. So I'm going to write that equation this way. It was just slightly simplified compared to the one I got upstairs. And doing a similar trick for the downstairs equation, I have C1 minus C2 on this side. Let's multiply both sides by root 2. I get a 2 times root 2/5. Right, or I could write it as root 8/5, I guess. And now I'm ready to solve for C1 and C2 just by adding and subtracting, right? So I would say that if I add these two equations, the C2's go away, and I get 2C1 is equal to the sum of these two, which is 3 times root 2/5. If I divide by 2, well, I guess I've got to simplify that. That means that my C1 is, let's see, let's put maybe everything under the root over there. So I get, if I divide by 2, I get the square root of 9 times 2, and I'm dividing by 2 over 4 times 5. I cancel this 2 against one of those. It looks like I get square root of 9/10. C1 is the square root of 9/10. Okay, and not surprisingly, when you subtract these two equations and do the same kind of stuff, it's got to be that these probabilities add up to 1, and so you get C2 is the square root of 1/10. You can check that with your work. It's not any more complicated than the C1 case. And that means if we're in this state, which we're describing in this sort of bias towards the Z direction kind of description, and we measure Sx, we get the plus h bar over 2 Sx value with probability 9/10, and the minus h bar over 2 outcome with only probability 1/10. Maybe it doesn't seem like it would be so skewed in one direction. Almost all the time you're going to get the positive eigenvalue. Certainly isn't clear to me that looking at this state, oh, I can see there's a lot of Sx equals plus h bar over 2 in there, and hardly any minus h bar over 2 Sx value in there. It's just not clear. You got to do the work and write it as a linear combination like that. Questions on that? I think that finishes up what was asked for, yes, on the worksheet. Those are the probabilities. All right, good. Here, just by the way, that was for a particular initial state. Here it is for an arbitrary initial state. It's really no more difficult in the arbitrary state, right? If I say, instead of 1 over root 5 and 2 over root 5, I just have an A and a B, I've got to solve this system, and you can easily solve it just in terms of the symbols. The spin up coefficient along the x direction is A plus B over root 2, and the spin down along the x direction coefficient is A minus B over root 2. And again, these are the chi plus x and chi minus x states. So if we want to write that as a linear combination, we can just see what it is. Okay. Let's now go to that other worksheet that's the multi-page one that is, I'm going to leave that result up there because you may find in answering the questions on the third part of this worksheet, these A and B expansion coefficients are actually helpful. So let's go to the third part of it, which is entitled, well, it has to do with spin. It's the last 3 pages of the worksheet, although the third page is mostly blank. The stuff at the top of the worksheet, I'll put this up there in just a second. So again, this is the multi-page worksheet that I've stolen from somebody else. That's why it's a little bit blurry. This stuff is just a preamble of everything we've been talking about with spin up here. But the information you need that pertains to this problem starts with the now let's try out a situation where the electron is known to be in the state chi plus. So that means it's in a state of definite SZ, right? It's in the state 1, 0 if you're writing it in this 2-element notation. And now you're going to be asked what happens if we measure various things and what are the associated probabilities and possibilities. So think about those, go as far as you can, but I'll probably stop after about 5 minutes and sort of close the loop on the first page there and make sure we're all thinking about things the same way. Yes. It, by well-defined is meant that there's only one possible outcome, right? If there are multiple outcomes with any non-zero probabilities, then we would say it's not well-defined. Yeah, that's peculiar to whoever wrote this worksheet. I'm not sure if that's common terminology, but I certainly don't always say it that way. Yes. Mm-hmm. Tanner, how's it going? Good. Jake, how's it going for you? We're on the third part of this. So we've done the first two parts, but yes, this part here. Okay. So we're starting there, and it's the 2 pages following that as well. Okay, let's talk about just the parts before the Roman numeral 3, the combined wave functions. The first few are supposed to be easy. So we're in the state chi plus. Another way of saying chi plus is, in our usual spinor notation, that's the state 1, 0. So it's definitely along the z direction. If we don't put an x or a y up there in parentheses, we mean along the z direction. It's a definite state, and this is the positive h bar over 2. That's what the plus means there. Okay, so it's all in that state at time t equals 0. And if we measure s squared, well, s squared is associated with the square of the total spin angular momentum. That's an immutable property of an electron that corresponds to little s equals 1/2. So in A, the only value for s squared is equal to s times s plus 1 h bar squared, and in this case, s equals 1/2. So that's 1/2. We've seen this several times. Times h bar squared. This is 3/2, so 3/4 h bar squared. If we measure the square of the spin angular momentum, we're guaranteed to get 3/4 h bar squared with probability 1. What possible outcomes are there for a measurement of SZ? Well, our state is all SZ equals plus h bar over 2. So the only possible outcome is SZ equals plus h bar over 2 with probability 1 is the answer to the first blank in B. I don't really understand the lettering here, but in any case, there's several parts to B. What possible outcomes are there for a measurement of SX? It says in the second part of B. Well, if that's true, I've got to do this. I've got to write 1, 0 as a linear combination of these two. And then the squares of the coefficients would give us the probability, right? So in this case, the second part of B on that first page that we're doing here, I want my A and B to be 1 and 0. And I'm going to try to write it as a linear combination of these two states of definite Sx. And from what I showed you on that, slide that I just took away, the coefficients ends up being just whatever A and B are. You do A plus B over root 2 and A minus B over root 2. So in this case, these are both 1 over root 2, right? In our case here, because A is 1 and B is 0. So the expansion coefficients are 1 over root 2. And therefore, the probability of getting the plus Sx eigenvalue is the square of this, is 1/2. So to summarize in the second blank, we would say Sx, we can either get plus h bar over 2 or minus h bar over 2. And the probabilities are the squares of these expansion coefficients. So each of those probabilities is 1/2. Probability 1/2 for each of them. And you'll find that it sort of makes sense that if you're in a state of definite SZ, whether it's 1, 0 or 0, 1, the probabilities are equal associated with each of the Sx values. It's also equal associated with each of the Sy values, because I could have just renamed my S-axis as the Y-axis. If you picked a Z-axis, any of the perpendicular directions could have been called X. Okay, here's the question Yi Chen was asking about. Is the X component of spin angular momentum well-defined for this electron? Again, well-defined means there's a unique measurement outcome value. In other words, there's only one thing with probability 1. No, the X component and the Y component aren't well-defined because there's going to be two outcomes with equal probabilities in each case. So neither one is well-defined in the way they're using that term here. The way we would refer to that is we would say, no, it's not in a state of definite Sx. Neither is it in a state of definite Sy. That's what the well-defined means. Okay, C is at the top of the next page. If you started with the state chi plus and measured Sz several times in a row, what might you measure? How about the first time you do it? Well, we already decided, I didn't write it down here, but the only Sz outcome with non-zero probability is Sz equals plus h bar over 2 with probability 1. When I make that measurement, it collapses to the state of definite Sz associated with plus h bar over 2. That's the same state. So you could think, we made a measurement, it collapses to this state, or it stays in that state if you like. And then I'm going to keep getting the same outcome over and over again. So I'm only going to get h bar over 2, even if I repeat the measurement over and over again. There's only one possibility. Okay, so we do that a few times in a row. It's still in this state after each time. We get the same value for Sc each time. Second question on the next page. Now suppose you measure Sx and get the result minus h bar over 2. What's the state of the electron immediately after the measurement? I guess there's a question of how you're going to specify that state, but I could specify it in two-element spinor notation, the way we've been doing it, right? If we measure minus h bar over 2 for a measurement of Sx, how would you write the two-element spinor that it collapses to after that measurement? There's a collapse of the wave function associated with each measurement.
Just be the one we're referencing.
Yeah, it's going to be when we get a definite value for Sx, here Sx equals minus h bar over 2, it collapses to the corresponding state that corresponds to that eigenvalue of Sx. So here is the state corresponding to minus h bar over 2. definite Sx value, and here is the corresponding eigenvector to that eigenvalue. So the answer to that second question in C, one way to answer it is just to say this state right here. Or you could write it this way. That's another way of specifying the same state, just different ways of answering the same thing. Questions on that? All right. Following the previous part. Okay, so we've just measured Sx. We now measure Sz. Following on our Sx measurement, we get minus h bar over 2. Now we measure Sz after that. What do you think the answer is going to be, even without doing the work? Yeah, there are two possible outcomes. What about the probability? So the two outcomes are plus h bar over 2 or minus h bar over 2. Those are only two possible outcomes always. Now, one of the probabilities might be 0, but what do you think the probabilities are for those two outcomes here? Half and half. Every time you're in a state of some definite direction measurement of Sz or Sx or Sy, if you measure one of the perpendicular components of S, then you're always going to get equal probabilities for the two possibilities in that case. We showed that explicitly here, but it works symmetrically. You know, of course, if I'm in a state of definite Sx and I measure Sz, I better get the same things as if I'm in a state of definite Sz and I measure Sx, which is what we've answered, because the only difference is which one we labeled X and which one we labeled Z. It can't be different probabilities associated with that. So I would answer D as the possibilities are plus or minus h bar over 2 with probability 1/2 each. That's what I would expect. You know, we didn't do the proof there, but you know, it's got to work out that way. And you could, well, okay, I guess it's easy to do, right? And we would say, if I want to do it, I would say I'm in this state, 1 over root 2 minus 1 over root 2. And I've got to write that as a linear combination of the states of definite Z, Sz. Well, what do you think A has to be? Oh, well, it's got to be 1 over root 2, right? What do you think B has to be? Well, it's got to be minus 1 over root 2. When I square both those numbers, I get 1/2. So you could even justify it to yourself in one line there, because these are the states of definite Sz values corresponding to the two eigenvalues plus or minus h bar over 2. Okay, let's take a little bit more time and think about part 3 now, which is putting in the spatial part. So we're saying we are going to write our overall wave function, or our overall description of a state is going to be a product of a function of r, theta, and phi. We're still in spherical coordinates because we're doing the hydrogen atom electron description. But then we're going to supplement that. This doesn't tell us anything about the spin state. We're going to supplement by also writing it by a 2-element column vector here, which describes the spin state. And of course, there are lots of different probabilities, right? Associated with these, I have my N, L, and M sub L quantum numbers. And associated with this one, I've got my S and M sub S quantum numbers. And here you're told at time t equals 0, it's in a very simple linear combination. Of course, it could be in a really complicated linear combination, but here it's just a linear combination of 2 of those product states. One which has a chi plus on the end and one which has a chi minus on the end. Remember, this is what chi plus means in 2-element notation. This is what chi minus means in the 2-element notation. So think about the probabilities they're asking for in those last few parts, and we'll go through those. Okay, looks like some of you are done, so let's go through them together. Here I've just rewritten what you're given at the top of part 3, just by, you know, they factored out the R21, but that just means that you're in the state R21. That means n equals 2, L equals 1. So, you know, if I were to, maybe it would help me to kind of simplify here for each of these terms. Let me write down all the quantum numbers I can see. This is NL, so n equals 2 in this state, L equals 1. This is LM, so that means M, I'll put a little L on it because we now have an M sub S too. M sub L equals 0. Chi plus, that we're describing an electron, it's a spin 1/2 particle, so that means S equals 1/2 always for an electron. This is a hydrogen atom electron. And M sub S is equal to, it's the positive of the two possibilities, and it's either plus 1/2 or minus 1/2. So in this case, the plus tells us it's a plus 1/2. And similarly for this term, I get n equals 2, L equals 1, M sub L equals 1. S, of course, has to be 1/2, and M sub S is minus 1/2. Okay, now I can, you know, just by inspection, kind of answer a lot of these. If we measure capital L squared, what possible outcomes are there? Well, I look in both these terms. The relevant quantum number is little l, and it's 1 for both of them. So that means the only possible outcome is associated with little l equals 1. The associated value for the square of the total orbital angular momentum is L times L plus 1 times h bar squared. So if I plug in 1, I get 2 times 1, or 2 h bar squared. Probability 1, only one possible outcome. What possible outcomes and associated probabilities are there for measurement of LZ? What do you say for this one, Mackay? Right, LZ is associated with the quantum number ML, and M sub L, or back in that section, Griffith was just calling it M, but to keep them straight here, we'll call it M sub L. The possibilities are M sub L times H bar, so we either get 0 H bar or 1 H bar. And what are the associated probabilities? 1/6 and 5/6. I take the expansion coefficients, which are circled here, and I take the magnitude squared of those, right? Magnitude squared of this is 1/6. That's associated with M sub L equals 0. And the magnitude squared of this, you know, the I gets multiplied by a minus I, which gives me 1. I get 5/6 when I square it. Of course, they add up to 1. You do all possibilities for that measurement, you should get, they sum up to 1. That's B. Questions on that one? C, what possible outcomes are there for a measurement of S squared? Well, there should only be one possibility because we're talking about an electron. That's S equals 1/2. And so S squared, I know we've done this many times. The associated value of S squared is S times S plus 1 times H bar squared, which is 1/2 plus 1, that's 3/2 times 1/2 is 3/4 H bar squared. Probability 1. And D, what possible outcomes and associated probabilities are there for a measurement of SZ? Well, the possibilities are M sub S times H bar. So H bar over 2 or minus H bar over 2. And the associated probabilities are the squares of the expansion coefficients. So H bar over 2 with probability 1/6 minus H bar over 2 with probability 5/6. Okay, you'll notice that nothing we're doing on this worksheet is hard at all in terms of calculations. It's just you need to keep straight all the little indices on there and remember how the quantum numbers are associated with physical quantities, how you express them in terms of H bars and whatnot. Well, on mine, I thought there was an I. Are you saying that's not on your worksheet? I didn't, I copied this worksheet from someone else, so I didn't write the worksheet. And, just I think to beg the question of like, well, what do you do if there's an I in there? Doesn't that confuse you? No. It's still just part of the expansion coefficient, as long as you know how to take the magnitude squared of a complex number. It's fine. And those expansion coefficients, the associated magnitude squareds better add up to 1, and they do in this case. Okay, good. But yeah, I should say, it's of course, it's going to be a different linear combination if I put 1 there. But in this case, all the quantum numbers associated with these are going to be the same, and the outcome probabilities and possibilities would all be the same if there were a 1 there instead of an I. It's just that if you put in the time dependence associated with this, so if you knew, maybe we say the Hamiltonian doesn't have anything to do with spin, we're going to talk about a case now or next time because we just got a couple of minutes left. If we assume the Hamiltonian doesn't have anything to do with spin, so we just talk about our good old hydrogen Hamiltonian, then to put in the time dependence of this, I need to put in the corresponding, factor. And I've got, in this case, the energies are the same associated with both of these, but the fact that if there's an I out here or a 1 out there, that's going to make a difference in terms of how it evolves with time, because these two terms would either be in sync or not in sync. So it has even though it doesn't affect the measurement probabilities, it is going to slightly affect how things evolve in time. Okay, good. So if you have more questions on that, or if you missed part of it from class, definitely ask me about it. It's due Monday now, that sheet. So make sure you write it up to your satisfaction, and we'll look at that. And let me just indicate where we're heading tomorrow. No, this is not the last subsection of chapter 4. This is just the middle part. We're going to talk about an electron in a magnetic field, because our Hamiltonian so far hasn't had anything to do with the spin state. But of course, we can have the energy of a state have to do with the spin state if we put our electron, which is in this potential associated with the proton that's sitting at the origin, in a magnetic field, because electrons have, just like they have angular momentum, because we think of, at least in the classical picture, there's some mass circulating in a circle as it spins around. That gives it spin angular momentum. We're told that we can't really think about that picture, but it also has charge. And so there's charge spinning around that gives it a magnetic moment. And you know that magnetic moments, when you put them in magnetic fields, tend to like to align with the field. So if I put an electron in a magnetic field that's pointing in the plus z direction, the spin up direction, well, I guess I got to think about this. The spin down direction is actually going to have lower energy because it's a negatively charged thing. And so when it's spinning in this direction, I really have negative charge spinning in that direction, which gives me a magnetic moment pointing in the opposite direction. But we're going to think through that magnetic moment. I don't know how much you guys have in your head what you learned in Physics 230 about magnetic moments, but we'll just remind ourselves of a simple model of it, of a current loop, and figure out what the force on it is if you put it in a magnetic field, and what the torque on it is if you put it in a magnetic field. And then we're going to say, well, let's just think of an electron kind of the same way. It's a ball of charge that's spinning, and so it's kind of like a current loop, and it's going to experience torques. And if it experiences torques, it's going to have a higher potential energy in one orientation and a lower potential energy in another one, where the torque has twisted it the way it wants to go. So we'll start with that tomorrow. See you then.
Have a good day.